Hi, my name is Manish Gupta, and in this video, I'm going to talk about BitNet, which is about scaling one-bit transformers for large language models. This is recent work from Microsoft Research. So let's get started. What is BitNet and what is its architecture? Right. So as all of us know, large language models are pretty large in size, and they also mean that they take high energy, right? So they involve high energy consumption, both for training as well as for inference. Can we sort of reduce this energy consumption and still reap the benefits of the accuracies that we can obtain from large language models? BitNet is a step in that direction. It is basically a one-bit transformer. Okay, so look at details, but practically, it tries to have weights with 1 bit rather than actually expressing them as 32 bits or 16 bits or 8 bits and so on. Okay. Um, in fact, it replaces the nn.Linear layer with BitLinear, which is basically the architecture for BitLinear is right there. And then BitNet architecture is right there. Of course, BitNet is after all a transformer, so it is still going to have the self-attention sublayer and the feed-forward sublayer. However, in the sublayers, as you notice in the self-attention sublayer, the multi-head attention basically has these linear projections so as to get the QKV, matrices or other QKV vectors. So those basically now are replaced using BitLinear rather than using nn.Linear. Similarly, there is a BitLinear out there. And then similarly for feed-forward network, there is a BitLinear layer rather than having the nn.Linear layers. Okay. So essentially in the BitNet network, the only essentially, you use low precision binary weights. So which basically means that if you have a weight which is positive, it basically, it's just represented as +1. If the weight is negative, it's represented as -1, right? So essentially this is what you do. So, you look at the weight. If it is +1, you make it, or rather if it is greater than 0, you make it +1, else you make it -1. Okay, but you do it only with weights. For the activations, well, the activations are basically 8-bit quantized. So activations, meaning the input and outputs, basically they are 8-bit quantized, where you quantize them in this range of -QB to +QB, where QB is 2 raised to 8 minus 1. So 8 bits basically being used here, right? So that's the number of, 2 raised to 8 minus 1 is the number of bins that you will quantize them to. For optimizer states and gradients while training, you actually use high precision so that finally you end up with reasonably competitive model. You preserve the precision for input and output embeddings. I mean, essentially using 8-bit quantized activations in that senses. Now, to make it really nice, they actually also do this model parallelism with group quantization and normalization. So of course, there are so many formulae here, and I'll talk about the details about these formulae. But then the idea is that you can still support these this entire training by doing model parallelism. Okay, so let's get into some more details about how this BitLinear is implemented. Okay, so basically broadly in the BitNet architecture, you essentially have binary weights and 8-bit quantized activations. Okay, so to do that, you essentially start with the input. So a BitLinear layer starts with the input and then does a layer norm, so that basically you have similar kind of a variance in the output as you would expect without quantization and without these binary weights. Okay, so you do a layer norm, which is also represented using this ln operation here, right? And then you do some quantization. So this quantization is on the input side. So you basically take the inputs, and remember inputs are also 8-bit quantized. So you quantize them, right? And then you multiply with this binary weights, and then you dequantize so as to basically get those outputs. Okay. Now, while doing this, the first step that you need to do here is to basically take your weights, the full precision weights, and then you basically shift them such that they have 0 mean. So you basically subtract alpha from these from the weight matrix, where alpha is essentially nothing but the mean over the entire weight matrix. So alpha is the mean over the entire weight matrix, right? Where the weight matrix is of dimensions n cross m. So you basically subtract that alpha. Now you have these 0 mean weights, and then you basically just apply this binarization. So you basically put a +1 when the weight is positive, or a -1 when the weight is negative or equal to 0. Okay, so that basically gives you your binarized weights. Okay. Now, how does the entire BitLinear layer work? So that's basically expressed in the formula here. So you essentially take the input, and then you have normalized the input. So you have done layer normalization. And how have you done layer normalization? Well, you have done it using this formula. So essentially, you take the mean of the input and the variance of the input and add a small epsilon so as to avoid zero values and so on. Okay, so you normalize the input and then you quantize the input using what is called as absolute max quantization and what is also expressed here. So to quantize the input, remember you have to quantize it in 8 bits. So therefore you have this QB value, which is basically 2 raised to 8 minus 1. And then you have a gamma normalization factor, which is basically, making sure that the L infinity norm for this particular X input, that's basically gamma, right? So as to essentially ensure that you're doing dynamic normalization based on specific inputs. Okay, dynamic quantization based on specific inputs. Okay. So that's that. So essentially, you do this absolute max normalization. So first step, you do absolute max quantization, right? First step, you start with the input, you do layer normalization, do absolute max quantization on top of it. And that basically gives you quantized input X. Okay. Now you multiply by the binarized weights, multiply by the binarized weights. And finally, to dequantize, this is what you do. To dequantize, remember you used gamma out there, the gamma guy here. You basically multiply by gamma again, so that makes sense, and divide by QB because you multiplied by QB here anyway. So that also makes sense. But then to maintain the same variance, you also multiply by this interesting factor called as beta, which is essentially L1 norm, average L1 norm of, or other, in some ways, average L1 of your weight matrix. Okay, so that's that. So let me summarize, how this thing is done as such. So the way this thing is done, in fact, this is the main formula, right? So in this main formula for BitLinear, this is how the output of BitLinear is computed. Okay. So to compute the output, of course, you need to take the input and multiply it with the weight matrix. So the weight matrix here is 1-bit quantized weights, 1-bit quantized weights that you see there. Okay. And then, so before you actually multiply by the weights, what you do is to essentially take the input, layer normalize it, add a max, quantize it, and then multiply by the weights. So take the input, layer normalize it, add a max, quantize it, and then multiply by the weights. And so that is basically this. This is the pre-processing for the inputs, multiply by the weights, and then final step dequantize. So final dequantize step is basically there, where you're essentially multiplying by gamma divided by QV, but also to maintain the variance, you're also multiplying by the factor beta, where beta is basically the L1 norm of the weight matrix averaged out. Okay, so that's how basically the BitNet works, and the BitLinear layer in BitNet actually works. Okay, so how does BitNet perform? So you might think that this idea of representing weights rather than 32 bits using just 1 bit might be very crazy, right? So this idea, by the way, has been tried earlier on CNNs and so on, but this was probably the first time that people have been trying it on transformer networks. So how does it work really, right? So to be able to understand how does it work, first let's compare it with other traditional other baseline methods that have been proposed earlier, right? So in this plot, what you see on the x-axis there is inference weight bits, and on the y-axis there is training weight bits. Okay, and the earlier methods, of course, most methods typically use this FP16 BF16, which basically means training and testing all of them done in 16 bits, right? BitNet is special because at train time, at inference time, it basically uses 1 bit. Okay, so that's how BitNet compares with the standard training or inferencing for transformer-based models. But there have been methods where you do training still in the 16-bit world, like smooth quant, GPDQ, and QUIP, where you do training in the 16-bit world, but you do inference in 8-bit, 4-bit, 2-bit world. Okay, nobody has still attempted to do inferencing on the 1-bit world. Okay, so these methods are called post-training quantization because the training is actually done in 16 bits. Unfortunately, people have observed that if you're basically using these post-training methods, your accuracy across several tasks really decreases significantly when you do like 1-bit quantization. Okay, so original accuracy might be something like 56, 57, but then at the end of it, if you look at the 1-bit quantized model, it'll basically be something like 45, 44, 45. Okay. On the other hand, BitNet really maintains that accuracy. Isn't that great? So BitNet basically, even at 1 bit, essentially you have almost the same accuracy as you would obtain from the state-of-the-art post-quantization model when you're using 8 bits in that senses. Okay. So that's that. Now, talking about the computational efficiency of this BitNet model, W1A8, basically meaning 1 bit for waits and 8 bits for activations, that kind of model. What do you observe? And these computational efficiency have been measured on two kinds of processors, 7 nanometer and 45 nanometer processors, okay, for multiply and add operations, right? So basically, here is a comparison on three different model sizes, 6.7 billion, 13 billion, and 30 billion model sizes, comparison between transformers and BitNet models, okay? So what you see, and transformer models are basically, they can be 32-bit transformers or 16-bit transformers. Of course, what you observe is 32-bit transformers basically take a whole bunch of energy in expressed in joules, right? Now, if you basically look at these bolded numbers, which are for BitNet, you can clearly observe this energy savings from BitNet compared to 32-bit or 16-bit transformer models. Okay. Now, going into a little bit more detail, how does BitNet compare with, let's say, 16-bit transformer models in terms of zero shot or few shot performance across several benchmarks that they compared with? You can read about the benchmarks in the paper, right? So this plot basically shows you zero shot performance. This shows you few shot performance across several tasks, right? X-axis is energy consumption and y-axis is accuracy. Okay, so note that energy consumption for 16-bit transformers is way higher, significantly higher, right? So what you observe is that if you compare across these, so BitNet, the orange curves basically can reach very good accuracy values. Okay, if you train them more. So the nice point is that if you keep training them, if you keep pumping in more and more compute, you do observe that the BitNet's accuracy can actually be super high. Now, this is something that is non-intuitive, right? How can single bit weights be so awesome? But it turns out that empirically people have observed that if you keep training, put in more and more compute while maintaining low energy consumption, because you do more iterations, but it turns out that doing more iterations does not really take more energy because you're doing bitwise operations now, right? So if you keep training, what you observe is that your BitNet model can actually give you at lower energy consumption better accuracy values. Now, isn't that magical? I mean, it's actually pretty interesting, right? At lower energy consumption, you actually get higher accuracy values, even with zero shot or few shot settings, either way. Okay. Now, here are some other plots which tell the story even better, right? So essentially, as you increase the model size, and if you basically keep the compute the same, you're basically not doing more epochs and so on. If you keep the compute the same, increase the model size, you basically observe that the loss actually decrease for BitNet also. Okay, which is great because one would intuitively not expect the loss to decrease too much with model size increase, but it does increase. But the loss does decrease even with BitNet, just like it does for FP16 transformers. Okay, this basically tells us that yes, BitNet 1-bit transformers also have this promise of coming up with the better accuracy, as you see on the left plot also, and lower loss as you increase the model size. Okay. Lastly, this plot basically just shows you if you increase the energy consumption, or other, yeah, I mean, you do more and more training, right? How well does the loss decrease? How well does the loss decrease? And as you observe, the loss decreases significantly at much lower energy consumption for BitNet compared to FP16. Okay, compared to FP16 transformers. And of course, this is of course very, very synonymous with the kind of accuracy increase that you see. That with much lesser energy, you can actually get better accuracy with 1-bit transformers. Okay, so you can read up this paper to explore more. But in short, in this video, I talked about BitNet, which is a 1-bit transformer. It involves low precision binary weights, just 1 bit for every weight, and 8-bit quantized activations. BitNet sort of achieves competitive accuracy while substantially reducing the memory footprint and energy consumption. Okay. Thank you for watching. Hope you liked the video. Connect with me on my LinkedIn or look at my search on my homepage. Thank you.